In today's lesson, we're going to look at something called rationalizing the denominator of a fraction. A lot of big words in there. The best way of looking at this is go ahead and throw you into an example. If I take the square root of 2 and divide it by the square root of 3. Notice we have a fraction, because we have radical 2 over radical 3, but we want to rationalize it. Well, if we look at radical 2 over radical 3, we can't simplify this because nothing will go into both 2 and 3. But what we don't like in mathematics is having a radical in our denominator. What we like to do is have a nice whole number down there, or integer value. So what we're going to do is we're going to multiply this fraction by some arbitrary radical in order to make this a non-radical in our denominator. And we want to do that the simplest way possible. Well, we're going to start by multiplying it by a radical, and we're going to think about this 3. What can we multiply 3 by to make it a perfect square, since our index is 2? Well, in this case, if we multiplied it by the square root of 3, square root of 3 times the square root of 3 would give us 9, and the square root of 9 gets us back to 3. So in order not to change the meaning of our original fraction, we have to multiply by radical 3 over radical 3. Remember, this reduces to 1, so we're really not changing the meaning of this, we're just changing what it looks like. We're going to go ahead and multiply these two fractions together now. I'm going to multiply radical 2 to radical 3. Remember, we're going to multiply those inside numbers together, so we get radical 6. And the same thing on the bottom, we're going to multiply those two inside numbers together, and we get the square root of 9. We're going to go ahead and clean this up now by simply reducing each of our radicals if we can. Square root of 6 does not have a perfect square in it, but the square root of 9 does. So we get 3. So our final answer is radical 6 over 3. Remember, as in multiplication, we cannot divide outside numbers with inside numbers. So don't try to reduce the square root of 6 over 3. It just doesn't happen. And there's our final answer. Now in example 2, let's go ahead and change that index. Let's say we have the third root of 3 divided by the third root of 5. Notice again, we cannot reduce those radicands at all. So we're going to go right into our multiplication of a fraction so that we get rid of this radical in our denominator. Since we're looking at the third root, all of our indices have to be 3. And we're looking to say, what multiplies to 5 to make us a perfect third power, or a third root? Well, in this case, if we multiplied by 25, we would end up with 125, which is a perfect third. You can think about this. This is 5 to the first. How many more do we need to add on to this exponent to make it divisible by the index? So in other words, what do you add to 1 to get to 3? And we would get 2. And 5 squared gives us the 25. That's how we can come about that number fairly easily. So we're going to multiply by the third root of 25 over the third root of 25. Our tops, we're going to multiply that 3 and that 25, and we end up with the third root of 75 divided by the third root of 125, which is 5 times 125, reducing as much as we can. The third root of 75 does not reduce anymore, but the third root of 125 is 5. Remember, we took 5 to the first times 5 squared, or 5 to the third, to get 125. And the third root of 125 is 5. And there's our final answer, the third root of 75 divided by 5. Again, don't try to divide these into each other, since we can't divide a radicand by a whole number. You have to divide radicand by radicand. In example 3, let's go ahead and look at a little more complicated example, say we have the 3 times the square root of x to the 5th, and let's divide it by the square root of 3x squared y. Well, now if I go ahead and look at this, what I would like to do to start is remember, if we have a radical over a radical, we can write that as a single radical. And if you remember, we were able to simplify within that. And I would like to go ahead and do that now without writing it as a single radical. So what I would do is take my x to the 5th and my x squared. I can divide those out by subtracting the exponents. So I end up with 3 square root of x to the 3rd over the the square root of 3y. Now, what I like to do is simplify my radicals if possible. So I'm going to take my x to the 3rd. To clean that up, I can break this up into x squared times x. And my x will come out. So I have 3x radical x over the square root of 3y. Now, we're going to go ahead and multiply by a radical in order to get rid of that radical in our denominator. So what do we multiply radical 3y by to make it a perfect square? Well, 3 times 3 would give us 9, and y times y would give us y squared. Remember again, we're looking at those exponents. We have 1 and 1 inside. Our index is 2. So what do you add to 1 to get to 2? Well, we add a 1. And we will add the y to the first to get to the second, another y to the first. So we're going to multiply the top by 3y as well. Now if I multiply these two together, I have a 3x on the outside, which is going to carry over. And my inside, I have radical x times radical 3y. Writing that in descending order, I get 3xy's. On my bottom, I'm going to take the square root of 3y times the square root of 3y and get the square root of 9y squared. Our square root of 9y squared will reduce for us. So we have 3x square roots of 3xy over 3y. And finally, we can reduce. These are both outside numbers, so I can cancel those. And I end up with x over 3xy over y. Remember, we can't reduce these y's because we have an inside number and this an outside number. Or one's a radicand and the other is not. And there's our final answer. In example 4 here, our problems can get quite nasty, quite ugly, and quite complicated fairly quickly. So let's take the 3rd root of x to the negative 2nd, y to the negative 4th, over 2. Notice we're taking the 3rd root of all of this. Well, we should see that we have negative exponents and we have fractions. So the first thing we want to do is go ahead and clean up those negative exponents. Remember, if we have negative exponents on the top, they're going to go to the bottom of our fraction to become positive. Well, if they both go to the bottom, we're going to be left with the 3rd root of 1. And what I'm also going to do is break up this fraction. Just like we could write fractions of 2 radicals as a single radical, we can break up the fraction of a single radical into 2 radicals. So we have the 3rd root of 1, and on the bottom our 2 is staying there to the 3rd root, but our x to the 2nd and y to the 4th are coming down to meet up with that 2. So we get the 3rd root of 2x squared y to the 4th. Now if I clean this up, the 3rd root of 1 on the top is still 1. The 3rd root of 2x squared y to the 4th, I can clean up y to the 4th, which is y to the 3rd times y. Remember, we want that exponent to be divisible by the index. So we end up with y 3 third roots of 2x squared y. Now we can go ahead and multiply to rationalize this denominator. So we ask ourselves, what do we multiply the third root of 2 by to make it a perfect third root? Well, remember this is 2 to the first, so we're going to add on 2 squared, which is 4. If I look at x squared, to make it a perfect third, I'm going to add 1 to it. So I'm going to multiply by an x. And to get my y to have a perfect third, right now there's y to the first, so I'm going to add on y to the second. Now if I multiply across, 1 times anything gives me, what's that radical? 4xy squared. And my bottom, I have y times the third root. Sorry, these should be all to the third roots. 2 times 4 gives me 8. X squared times x gives me x to the third. And y to the first times y squared gives me y to the third. Now I can go ahead and simplify this. My top is going to stay the same, the third root of 4xy squared. And on bottom, the third root of 8 is 2. The third root of x to the third is x. The third root of y to the third is y, but I already have a y out there, so I get y to the second. Remembering I cannot divide into a radicand if I don't have a radicand to start. So there's my final answer. Now let's go ahead and look at example 5, where we're going to bring in the conjugate. Here, let's go ahead and take 3 minus the square root of 2, divided by 2 plus the square root of 5. Notice here we have a binomial now on the bottom. We have 2 plus the square root of 5. I have to think of a number that I can multiply this by in order to get rid of that radical. Now, in our previous problems, we always multiply by what was under that radical. But if I were to multiply this by radical 5, I'd have 2 radical 5 plus the square root of 25, which removes this radical, but I end up with a radical here. You don't need to write this down, but again, if I were to multiply by radical 5 over radical 5, I would end up with 2 radical 5 plus the square root of 25. If I multiplied that radical 5 into both of those terms. So we can't do that. That's where our conjugate comes in at. So rewriting my problem here, remember the conjugate is simply taking and changing that sign. So if I were to multiply by 2 minus the square root of 5, which is the conjugate of this, remember that's similar to our difference of squares, where our middle term canceled. And that's going to be beneficial here, because if you look, our first 2 terms are going to give us a whole number, and radical 5 times radical 5 is going to give us a whole number as well, and then our 2 middle terms are going to cancel. Let's go ahead and look at how that looks on paper. So we're going to first multiply the tops together. So we're going to distribute this 3, just as we did in multiplication of binomial radicals. 3 times 2 gives me 6. 3 times negative radical 5 is negative 3 radical 5. Negative radical 2 times 2. I'm going to distribute my second in. So I get minus 2 radical 2. Negative times a negative is a positive, and 2 times 2 gives me the square root of 10. And I'm going to divide that. On the bottom, I have 2 plus radical 5 times 2 minus radical 5. Distribute my 2. I end up with 4. 2 times negative radical 5 is 2 radical 5. Radical 5 times 2 gives me 2 radical 5. And radical 5 times negative radical 5 is negative radical 25. Notice again, in my denominator, my 2 middle terms cancel each other out. The square root of negative 25 is negative 5. In my numerator, I have a lot of things happening. First, notice we have the same index, but my radicans are not the same, and they cannot reduce. So really, in the numerator, I can't do a whole lot of anything. I leave it as 6 minus 3 radical 5 minus 2 radical 2 plus radical 10, and that's divided by 4 minus 5, which is negative 1. Now, this negative 1 we can go ahead and clean up by bringing it to the outside or to the top. Remember, in a fraction, that negative can float between the top, the bottom, or out in the side, in the middle. So if I had 5 over negative 2, that would be the same as the negative of 5 over 2, which is also the same as negative 5 over 2. Notice how that negative can float from the bottom to the outside to the top. That's useful information to be able to do and simplify this problem. Here, if I had this negative on the bottom, I can pull it out to the side or bring it to the top. And what that's going to do is change each of these signs. So I'm going to take the negative of that entire numerator. So if I take that negative and distribute it through, I really end up with negative 6 plus 3 radical 5 plus 2 radical 2 minus the square root of 10. Notice how it changed all my signs. And there's my final answer. Not that it looks much nicer than what we started with. However, notice we did get rid of that entire fraction by getting rid of that denominator. Let's go ahead and look at one more example like that before we call it a day. So in example 6, I know you like more examples, so I'm giving it to you. Example 6. Here, let's take 3 minus 2 radical 7 divided by 10 minus radical 7. So to conjugate, or to look at our denominator, we have 10 minus the square root of 7. The conjugate of that, remember, we're going to change only the sign between the two terms. So it was a minus, we're going to change it to a plus. And our top is going to be 10 plus the square root of 7. I'm going to go ahead and distribute my numerator binomial to the other numerator's binomial. So we have 3 times 10 gives us 30. 3 times the square root of 7 is 3 radical 7. Negative 2 radical 7 times 10 is minus 20 radical 7. And negative 2 radical 7 times radical 7 gives me negative 2 radical 49. That's going to be divided by distributing my 10 through the bottom. I have 100 plus 10 radical 7. I'm going to distribute my negative radical 7 through. So I get minus 10 radical 7 minus the square root of 49. Now I can do a lot of things to clean this up. To start with, on the top, the square root of 49 is 7. And I have negative 2 times 7 gives me negative 14. So I have 30 minus 14 gives me 16. And 3 radical 7 minus 20 radical 7 is negative 17 radical 7. On the bottom, my middle terms are going to cancel. 10 radical 7 minus 10 radical 7 gives me 0. The square root of 49 is 7, so I have 100 minus 7, which is 93. Now what I'd like to do is to make sure that I cannot simplify this anymore. Remember, this kind of looks like the quadratic formula. So if I can take a number out of the top, 16 and negative 17, and divide it by a number that's in 93, I would want to go ahead and do that. Well, in this case, 16 and 17, we can't factor anything out, so we're going to leave it at 16 minus 17 radical 7 over 93. And that concludes our rationalizing denominators.